years. I don't know if you are interested in that topic. It's good for you to learn a little bit about just basic bit manipulation, they call it. So let's take an example. So let's say um, in, in in algebra, have they taught you things like different types of operations like and operation, or operation? Have they taught you any of those? Okay, that's good. Yeah. So we will be going into a little bit of that. It involves a little bit of simple algebra, like just again just like this, 0, 1, 2, that kind of stuff, and it's used all over the place. So if you look at um, a simple matrix like 0, 1, 0, 1, and then if you're doing like a operation on zeros and ones, because in computers, again, everything is stored as zeros and ones. So if you were to add two numbers, or you were to multiply two numbers, or you do any sort of operations, at the bottommost layer, it's important to know what it actually is using. So there are different operations. So there's the not operation, and or not, and then there's XOR, and so on. So we'll cover the first three because they're simple this week. Next week I'll talk, and I'll also explain to you why it's important, because almost all of electronics, there's this concept of switching, gate switching, where you actually kind of send a bit from zero. From one side you send zeros, another side you send one, and then it does a 0 and 1, and then it computes that value and tells you it's actually 0, because that's how the AND works. So the AND operation, the way it's defined in Boolean Algebra is 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. So the only one that actually gives you a value of 1 is when you do bitwise ANDing of 1 and 1. And this is very valuable to sort of know in the very long run when you're doing, like even say Java programming, or you're writing some sort of algorithms. People do these kind of things all the time, so you kind of get it better. The first time you just have to by heart it, but slowly you don't have to by heart. So we'll take the OR one. Sorry, OR, and then I'm going to say 0, 1, 0, 1. So in case of the OR, it's kind of like the opposite. Here it's, so the way OR, so one way to remember the AND is, you can say that unless both of them are 1, the answer is not 1. Both of them, for the answer to be 1, both the inputs have to be 1. That's one way to remember. So this and this has to be 1, only then it's 1. In all other cases it's 0, so that's one way to remember that. Yeah.
Is it like multiply, like 1 times 0 times 0 is 0, and 0 times 1 is 0, and 1 times 1 is 1?
Exactly. So now you exactly understood what I was talking about some time ago. So I don't know if I talked about registers yet, but in computers, in the chips, they define different operations like add, multiply, and so on. So the AND is equivalent to nothing but multiply. And but some of the others like add and others are more tricky, so we will not talk about that yet. But the way the OR operation works is at least one of them have to be 1 for the answer to be 1. So you think of this as just the opposite of this. Not exactly opposite. What I meant by opposite is, in this case, the way to remember this is you say that in order for the answer to be 1, at least one of the inputs has to be 1. If both are 1, then it's 1. But if both are 0, that's the only time it is 0. So that's the OR operation. And these two are called the binary operators. Why binary operators? Because there's always two inputs to see an output. And the not is actually a unary operator. So what is the meaning of unary? You don't need two operands to get the answer, so it's always applied on one. So the not operation is simple. You just say if it is 0, then you get 1. So not of 0, in other words, is 1. Not of 1 is 0.
Like the opposite?
So it's just opposite, yeah. So this is also very, there's actually a gate called the NOT gate. So in electronics, when you look at the circuits, there's a NOT gate, there's an AND gate, there's an OR gate. So they build all these different gates. These gates pretty much do nothing but what I just told you. There are many other gates, we'll talk about them next week. XOR, exclusive OR, and then there's the NAND gate. So the NAND gate is sort of like the AND gate, except after you do the AND, you do a NOT of that AND. So it's the NAND gate. So, but these are more basic, so I thought I'll first talk about them. And this whole topic, like I said, is still part of Boolean algebra, but it can be used in gate theory and electronics, many other fields. So once you know that, you can actually apply this, and even in Java programming, like if you learn programming and you're actually writing a lot of numbers. So I'll give you one example why this is good to know and why this might be useful.
I have a question.
Yeah, go ahead.
On the not thing,
Yeah.
why didn't you draw like the box right there?
Why didn't I draw a box, right? That's a
Yeah.
good question. So, like I said, this is a unary operator, and this is a binary operator. So unary means it applies only on one operand, so it's really just one input and one output. In this case, you had two inputs, like 0, 0 are these two inputs, this is the output. 0, 1 are two inputs, so 2 means binary. 1 and 0 are two inputs, you get one output. But in this case, all you're saying is not of 0 is 1, and not 1 is 0. That's all you're saying. So that's why it's the number of inputs are only 1, and that's why it's unary. So I think unary, the word again came from Latin, possibly meaning unit or just one. That's why it's unary. And the binary is the bi, and the bi typically means 2 in the Latin. So a lot of the computer, just like any other area, right? I mean, even the kilos, somebody tells you buy 2 kilos of bananas or whatever. So the kilo again is a Italian, a Latin unit to count either weight or any sort of magnitude, any number. So I was talking about the importance of just this whole concept of bits, using bits, and so I'll give you one example where in computer science this is useful. Can I get rid of this? Okay. Let me see how much time. Yeah, I think we started at 2:30, so we should probably be almost done. But I'll give you one example. So let's say you have the number 0, 0, 1, 0. And does anyone remember what this is? In terms of decimal, I mean.
Is 2?
2, yeah. Now, if I have, say, 0, 1, 0, 0, does anyone remember what this number is?
4.
4. So you're getting really quick at this. One way to do that is, as soon as you see 1 in the hundreds place, you just say 2 raised to 2. That's 4, and that's it. And so all I did is I shift left this 1 bit from here to here. I brought this 1 from here to here. And I actually kind of multiplied the number by 2 times. So a shift left, so if you think of a shift left as an operation, it is equivalent to multiplying by 2, right? And you'll notice this is true everywhere. So there are some tricks like that in computer science when people are doing any computation, they actually can use tricks like these to, you can double the size of a number if you know that it's already a power of 2. Now, what if you have a number like 0011? If you shift left, you don't necessarily get twice. You can try that. So, what is this equivalent to? What's the decimal? 3. Good. Now, if I shift left each bit 1, so I basically move this to this and this to this, so I do 0110. What is this number?
6.
6. So I was wrong, right? So it's basically, it's not just for this. When you shift left, you're actually multiplying the number twice, by 2, I mean. So you're actually using the shift left as a way to multiply by 2. So this particular thing is right. It's true in general. So you can use tricks like that.